Okay, we're going to be talking about simplifying radicals. A couple of things. We're going to start off with square roots and build up on some knowledge that you probably should have from Algebra 1. First of all, let's remember that the key idea is underneath the radical sign here is that we want to be trying to find perfect squares, perfect cubes, etc. And we need them to match the root index. Now, like we had talked about prior to this, the root index is the number right here in the corner of the radical. Normally you would see a number there for cube roots or higher. Square roots, since mathematicians are inherently lazy, just got dropped off. And so there is a 2 there. So after you so one of the ways that you can do this is that you can say, okay, well, I know that z to the 6th is the same thing as z to the 3rd squared. And so if that was the case, then that would just be the square root of z to the 3rd squared is just going to be z to the 3rd. And then that's what you're going to pull out in front. Now, another way that you can go through and do this as well is you can just go ahead and change it into exponential notation. So if I had this, you could also rewrite it. Now remember, the root index here becomes the denominator of the fractional exponent. So this would be like 1/2. This would be z to the 6th to the 1/2 power. So, and again, this is more steps than I would expect you to show, but just so you can understand what's going on, it'd be z to the 6th to the 1/2 power. Now remember, when I take powers to powers, then you're multiplying the exponents. So now I have z to the 6/2 power, which then of course becomes z to the 3rd. As another example, this is a little bit more involved, and I can show you what you can do if you have leftovers. So now our index is the 3rd, and I think I'm going to go ahead. So first thing we need to do is deal with the 128. Now, you may or may not know that that's 2 to a particular power. You can break it down a whole number of different ways. One of the ways you can always do it is go back to middle school methods, and you can just break it down into prime factorization until you see something that you know is a cube. But anyway, so you can go 2, start with the smallest prime 2 and say, can I divide 2 into 128? Yes, I can do that 64 times. Can I divide 2 into 64? Yes. 32 times. Can I divide 2 into 32? Yes. Now, if you ever get to the point of saying no, either the number that you have left over is going to be prime, or you just go up to the next highest prime. So in this case, then you would try 3s. Or I shouldn't say in this case, then you would go ahead and try 3. So you get 16. I can divide 2 into that, and I get 8. Divided 2 into that, I get 4, etc. Now again, at some point here, you may have already seen that you've got a cube, but regardless, 128 I can write as 2 to the 1, 2, 3, 4, 5, 6, 7th power. So this is going to be 2 to the 7th power. So one thing that we can do then is write this all as a fractional exponent. And again, I'm going to give you a couple of different techniques that may work here. Now again, remember when you're taking an entire product to a power, every individual part of the product, each factor is going to be taken to that power as well. So that's going to equal 2 to the 7/3 power, a to the 6/3 power, b to the 8/3 power, and then c to the 10/3 power. And then from there, some people had asked last week when we were dealing with fractional exponents about what do you do if you have an improper fraction. Because obviously a to the 6th is going to break down into a squared, because 6 over 2 is 3. However, like 7/3 is like 2 to the 2 1/3 power. B is going to become 2 to the 2 2/3 power. C is 3 to the 1/3 power. What you essentially end up doing then is you're going to take your cube root, that's going to stay, and the whole number part of the exponent is going to be, that should be, it looks kind of like a z, my apologies, is the whole number part is going to become the exponent for the number out in front. So in this case, this is going to become 2 squared. Now, what am I going to do with this 1/3? Well, remember the 3 is being taken care of by the root here. So that means I'm going to put 2 to the 1st power underneath my radical 3. B, I've got 2 full b's. So I'm going to go b squared there, and I've got 2 leftovers. The 3rd is already there, so I've got b squared. C is going to go to the 3rd power, and I've got c to the 1st power on the inside. So to simplify all of that out, then I would come up with 4a squared, b squared, c to the 3rd, and then the cube root of 2b squared c. And that would be your final answer. and it's quote-unquote simplified. Now, I know it looks a little bit more complicated than the original problem, but again, it's a standardized way of doing things. Now, another way that sometimes people will do this, which would kind of be the shortcut that I hope you would get to, is ask yourself, okay, how many times does 3 go into 6? Twice. Okay, so that's going to become 8 to the 6th power. How many times does 3 here go into the 8? Twice. So I get b to the second, but how many are left over? 2, so the leftovers again go here in the fridge. Oops, I just realized I forgot the cube here. And then you do the same thing. How many times does 3 go into 10? I get to do the third. The leftovers go here. So the only thing really then you have to worry about is the 128. For adding and subtracting radical expressions, the key idea here is going to be twofold. First of all, you must have like radicals to add them. And that's just going to be like having like variables. Once you get the radicals in all 3 parts to be the same, then you just go ahead and just add them all up. So in this case, I would suggest you look for the radical of the smallest number and see if that's simplified as far as you can. If it's not simplified, simplify it. But if it is, like in this case, then that'll give us a clue in terms of what this needs to become. So if I'm able to simplify this together, I'm going to need to come up with 3 cubes for all of this. So that means that, okay, well, can I get this down to a 3? Well, can I get this down to a cube root of 3? I can if I break this down into 8 times 3. So then I get 4 times, the cube root of 8 is 2. So then I get the cube root of 3, and then minus, and again I'm going to do this over here too. Can I break this down? Sure. Can divide out a 3, which would leave me with 27. So then that would be cube root of 27 is 3, and then I get cube root of 3. So now, as I said, it's like combining like terms. So how many cube roots of 3 do I have? Right here, this is now 8. Sorry, I thought I made the blue different color. Pardon me. So this is now 8 cube root of 3. So I've got 2 cube root of 3 plus 8 cube root of 3, which would be 10 cube root of 3 minus 7 cube root of 3. So that would become my final answer of 7 cube root of 3. So again, find the smallest, simplify all of the different radicals to the lowest terms, and then go ahead and combine all of those, just like you would with a variable. Multiplying radical expressions, you're going to go through and treat them just like polynomials. You treat this just like 2 binomials being multiplied together. So you do this double distribution. I'm going to go 5 times 5 and get 25. I'm going to take 5 times square root of 3 and get 5 square root of 3. I'm going to multiply a negative square root of 3 times 5. Now, some of you may have noticed that these are essentially conjugates. Conjugates, again, being like the factors of a difference of perfect squares. And that's indeed what they are. So I get then minus square root of 3 times square root of 3, which would be 3. I'm going to go ahead and write it as 3 squared just so we can simplify it a little bit nicer. So again, these will zero each other out. This becomes a negative 3. So then your final answer over here is going to become 25 minus 3, which is 22. Sometimes it's not going to all come out so nice and neat as that. It'll get a little bit messier, and that's okay. You've got 2 options here, by the way. You can either multiply this out first and then worry about simplifying the square root of 12, or you can worry about simplifying the square root of 12 right now. Since I know that this is going to break down into 4 and 3, I'm going to go ahead and change this to 7 minus 2 square root of 3 times 4 minus square root of 3. So when I multiply this out now, I can worry about this is going to become 2 times 3. So again, you're going to multiply out 7 times 4 and get 28. Multiply 7 times negative 3. Get a negative 7 radical 3. Multiply a negative 2 radical 3 times 4, so I get a minus 8 radical 3. And then do the same thing back here, and I'm going to get a positive 2, and then times 3, so square root of 3 times square root of 3 is 3. So that means that this whole number is now going to become 6. And then my simplified version is 28 times 3 is going to be 34. And then this negative 7 minus 8, since these have like radicals, are going to become minus 15 radical 3. Sometimes you're going to have like radicals, sometimes you will not. If you do not, you can't combine them, and that's all right as well. Just for general etiquette, rational numbers come first, irrational part comes second. And the last thing we need to talk about is how you rationalize denominators. Again, the whole reason for this is at one point it made the division easier. The whole key is, remember, no radicals are allowed down in the denominator. You cannot be divided by an irrational number. So then what we end up doing is we need to multiply this by the denominator by something that will make it, bring it back into becoming an integer. First thing I would do is break this down into two different radicals. So it's going to be square root of 9 over the square root of 7. So that's going to be 3 over the square root of 7. Now again, we can't multiply that by anything, or we can't leave the radical down at the bottom. But I do know that the square root of 7 times the square root of 7 is 7. So if I multiply the bottom by square root of 7, that would eventually get me over here to become a 7. So that's mission accomplished in terms of getting an integer back in the denominator. If I multiply the denominator by square root of 7, the top has to become multiplied by square root of 7. So I get 3 square root of 7 over 7. You do want to check to see if you can simplify this at all, in case you happen to miss something in terms of up here, simplifying it earlier, or sometimes radicals have different parts of similar factors, and that would help as well. Again, this is something you probably did a little bit in honors geometry, and I know you should have done back in Algebra 1. You probably didn't do anything with cubes back then. So what you end up doing here, again, split it up. So now I've got the cube root of 10 over the cube root of 9, neither of which are perfect cubes. However, I do know that if I can get the denominator out here to be, and then by the way, if you can break this down, 9 is 3 squared. If you factorize things as much as possible, that can save yourself some time later on because you won't have to simplify as much. I know that I want the cube root of 3 squared or 3 cubed down here, because the cube root of 3 cubed is going to be 3. So then you ask yourself, well, what am I missing in this part down here in the denominator that would get me to this? Well, I need it to be 3 cubed, it's 3 squared. So if I multiply it through by another 3 cubed, or 3 underneath the radical, then I've got my 3 cubed. And so again, you're just going to fill in the missing parts. What am I missing? What's going to work? So the bottom becomes cube root of 3 cubed. The top, 3 times 10, is the cube root of 30. So then my final answer, top doesn't simplify any further, so that's going to be cube root of 30. And the denominator is just going to become 3. The last, and if you had multiple variables here, actually, now that I think about it, let me do one more example quickly for you. Let's say if I did something like, if I had, let's say, the 4th root of 7 divided by the 4th root of 2w squared. Okay. Now I know that over here, I'm going to want the 4th root in order to make this easy to simplify. I would like it to be 2 to the 4th, w to the 4th, because if I can do that, that's just going to give me a denominator of 2w. So again, ask yourself, what's missing? All right, we'll get to get 2 to become 2 to the 4th, I need to multiply that through by 2 to the 3rd. All of this underneath the 4th root again. And to get w squared to w to the 4th, I need to multiply it by by w squared. Do it on the bottom, do it on the top. So I get 2 to the 3rd w squared. This new numerator now becomes the 4th root of, this is worth 8. So 7 times 8 is 56 w squared. And so then I get the 4th root of 56w squared all over 2w. So much like with some of the other things we talked about, if you've got multiple variables down here, treat each of the variables separately and say, okay, what do I need to deal with this variable to get to the 4th power? What do I need to do with this variable to get to the 4th power? Or whatever the index is on your root. Last thing, rationalizing denominators, is when you have a binomial down here. If you remember back from a couple of examples ago when we did this one where you get the conjugates, the radicals here drop out. And again, the conjugate here is when you've got the two different parts of the number, or two parts of the different parts of the binomial, and one's negative, or one's subtracting, one's adding. What that creates is this difference of perfect squares type of feeling where those middle terms will drop. So we're going to multiply by the conjugate. So the conjugate of 3 minus square root of 2 is going to be 3 plus square root of 2. And again, if I do it on the bottom, I'm going to do it on the top. Now, people tend to like this because, again, you can take the shortcut. If you want to multiply this all out, you can. But again, remember, the reason why we're doing this is so we can get the first term squared minus the second term squared. And that way we get rid of all the radicals. On the top, again, make sure you distribute this out to both parts. So I'm going to get 12 plus 4 square root of 2. On the bottom, this turns out to be 9 minus 2. So I get 12 plus 4 square root of 2 over 7. Now, you do want to check, I'm circling this, I guess, a little bit prematurely. You do want to check to say, okay, can I factor anything out of the top that I can divide out of the bottom? So I could factor out a 4 if I wanted to, though that's not going to be extremely helpful because 4 won't divide into 7. But again, you can do this with variables or anything else. The whole key idea here is whatever this sign is, take the same two terms, use the opposite. And that is all of the radical expressions skills in a nutshell. If you have any questions, obviously email or call, and I'll see you in class. Thanks.